Hi guys. So following on from the experiment that you did in class and the calculations that you've done based on your experimental results, what we're going to do today is practice some enthalpy of combustion calculations. So the first example in the pupil booklet says, in an experiment, the burning of 0.980 grams of ethanol resulted in the temperature of 400 centimeters cubed of water rising from 14.2 degrees to 31.6 degrees. Use this information to calculate the enthalpy of combustion of ethanol. So, before we calculate enthalpy of combustion, the first thing we have to calculate is how much energy is released when the 0.980 grams is burned. And to do that, we use EH equals CM delta T. So our EH is what we'll be trying to calculate. Our C is 4.18. Our M is the mass of water, which is 400. And we need to get that into kilograms, so we divide it by 1,000, 0.4. And our T is our temperature difference. So we're doing 31.6 take away 14.2. The temperature we finished on, take away the temperature we started with. 17.4 degrees. So now we can calculate our EH. So EH equals CM delta T, which is 4.18 times 0.4 times 17.4. times 0.4 times 17.4. $29, and I think we'll leave this number quite long until the very end. So 29.0928 kilojoules. And then we are trying to work out the enthalpy of combustion of ethanol. So the first thing we need to do is work out the formula for ethanol. So ethanol is C2H5OH. One hydrogen, 16 is the mass of oxygen, 1 times 5, and then we've got 2 carbons. So 1 plus 16 plus 5 plus 24 is 46. So the mass of 1 mole of ethanol is 46 grams. So we know that if you burn 0.980 grams of ethanol, we release 29.0928 kilojoules per mole. So if we burn 1 mole of ethanol, 46 grams of ethanol, which is 1 mole, we can do a cross multiplication to find out the enthalpy of combustion, or the enthalpy, how much energy is released when we burn 1 mole or 46 grams. So we do 46 times 29.0928. So we're timesing across the way, and we divide by this number up here, 0980. So 46 times 29.0928 divided by 0.8980 rather. Enthalpy of combustion is always negative, 1365, and I'll round to 2 decimal places, 0.58 kilojoules per mole, and that is our final answer. The second example in the pupil booklet says, to raise the temperature of 300 centimeters cubed of water from 24.3 to 40.2 degrees, 2.43 grams of butanol was burned. Use this information to calculate the enthalpy of combustion of butanol. So first of all, before we calculate enthalpy of combustion, we want to calculate how much energy was released when we burned this much. So we're using EH equals Cm delta T. EH is what we're trying to calculate. C is 4.18. The mass is the mass of water, not the mass of butanol, which is 300 divided by 1000 to get it into kilograms, 0.3. And our temperature difference is 40.2 take away 24.3. Which is 15.9. So we can calculate our EH. EH equals Cm delta T, which is 4.18 times 0.3 times 15.9. Is 19.9386 kilojoules. So that is how much energy is released when we burn this 2.43 grams, but we want to find out the enthalpy of combustion of butanol, so how much energy is released when we burn 1 mole of butanol. So we need to work out the mass of 1 mole. Butanol has this structure. So 4 carbons, 1, 2, 3, 4, 5, 6, 7, 8, 9 hydrogens, OH. Mass of hydrogen is 1. Mass of oxygen is 16. Mass of hydrogen is 1. Mass of carbon is 12. So we've got 12 times 4 plus 9 plus 16 plus 1 is 74 grams. So we know that if we burn 2.43 grams of butanol, we release 19.9386 kilojoules. And we're trying to work out how much energy is released when 1 mole of butanol is burned, when 74 grams is burned. And we times across 74 times 19.9386, and we divide by this number, 2.43. So 74 times 19.9386 divided by 2.43. So the enthalpy of combustion of butanol is negative 607.18. And I'm just going to do my units underneath because I can't fit them in. Kilojoules per mole. The first two that we're going to do are the questions from the pupil booklet. So you can try these questions on your own. Pause the video just now and try them, and then go through the solutions with me. And we're going to have 2 extra questions at the end as well. So if you could do all of these questions in your notes jotter, that would be perfect under a heading of enthalpy of combustion, so that you have plenty of examples to look back on. So for the first question, it says propane is burned to heat 250 centimeters cubed of water from 22.5 degrees to 31 degrees. Calculate the energy given out. Now, this is only a 2-mark question. It's not asking me for the enthalpy of combustion, just the energy given out or the energy released. So we're using EH equals Cm delta T. Our C is always 4.18, sorry. We're always using the volume of water, but as always, our water needs to be in kilograms, which is the same as turning it into litres. So we want to divide that by 1000. So we'll take our 250 centimeters cubed, divide by 1000 to give us 0.25. And we are also timesing that by our temperature difference. So we started at 22.5 degrees and we're going to 31 degrees. So we'll do 31, our finishing temperature, take away our starting temperature, is 8.5 degrees. And if we times that all together, 4.18 times 0.25 times 8.5, we get 8.88. Now, enthalpy of combustion is an exothermic reaction, so our enthalpy here will be 8 negative for an exothermic reaction because it's releasing energy, it's giving out energy, so it's a negative value. So negative 8.88 kilojoules. That is our final answer. For question 6, it says a massive 0.32 grams of methanol is burned in a spirit burner, which is used to heat up 200 centimeters cubed of water from 19.5 to 27.5 degrees. Calculate the enthalpy of combustion of methanol. So we are having to do two steps here. First, calculate the energy released. Secondly, calculate the enthalpy of combustion. So first of all, I'm going to be using EH equals Cm delta T. So I'm trying to find EH, the energy released. My C is always 4.18. My mass, I've got 200. I need to get that into litres, so I'm dividing it by 1000 to get 0.2. And my delta T is my end temperature, take away my starting temperature, which is 8 degrees. So for my EH equals Cm delta C calculation, I've got 4.18 times 0.2 times 8, which comes out at 6.688 negative kilojoules. And my next step is I'm calculating the enthalpy of combustion. So what I've calculated here is the energy released when I burned 0.32 grams. For enthalpy of combustion, remember the definition is the energy released when you burn 1 mole of a substance. So we need to figure out first what is the mass of 1 mole of methanol. Well, methanol's chemical formula is CH4. The mass of hydrogen is 1, we've got 4 of them. The mass of carbon is 12 and we've got 1 of them. So 4 plus 12 is 16 grams. And then what I'm going to do is I'm going to set up a cross multiplication. So I started off my experiment with 0.32 grams, and when I burned that released 6.688 kilojoules per mole, or kilojoules rather. So the question tells me I burned 0.32 grams, and I calculated that that's how much energy I released. And I calculated that that's how much energy I released when I burned that 6.88, when I burned that 0.32 grams. Now, to work out the enthalpy of combustion, I have worked out that the mass of 1 mole of methanol is 16 grams. So to work out how much energy which would be released when I burned 16 grams or 1 mole, you cross multiply, so 16 times 6.688, and you want to divide that by 0.32. So I'm timesing across and dividing by the one that's left. 16 times 6.688 divided by 0.32. So my enthalpy of combustion of methanol is negative 334.4 kilojoules per mole. So again, the answer is negative 334.4 kilojoules per mole. So we're now on to our final question today, our extra practice question 4. The enthalpy change when 1 mole of methanol is burned is negative 24.6 kilojoules per mole. Calculate the mass of methanol, which would produce a temperature rise of 9.20 degrees C when used to heat up 25 centimeters cubed of water. So for this question, we're not being asked to calculate the enthalpy or the enthalpy of combustion of 1 mole. We've already been given that. We've been given that when 1 mole of methanol is burned, negative 24.6 kilojoules per mole of energy is released. That is the enthalpy of combustion. The question is asking us for the mass of methanol, which would cause a temperature rise of 6.20 degrees C. So, first of all, what I want to look at is the mass of 1 mole of methanol, which is 16 grams. So I know that 1 mole of methanol, or 16 grams of methanol, results in a 24.6 kilojoule per mole release of energy. So if I want to work out how much mass of methanol would cause a 9-degree rise, first of all I need to work out what energy is associated with a 9-degree temperature rise. So I'm working out EH. My delta T is 9.20. My mass of water is my mass of water is 25. I'm dividing that by 1,000 to get it into kilograms, so 0.025. And my C is 4.18 because we're heating up water, and that is the heat capacity of water. So if I work that out, EH equals Cm delta T, 4.18 times 0.025 times 9.20. I work out that the energy needed is 0.9614 kilojoules. So to heat up my water by 9 degrees, to heat up my 25 centimeters cubed of water by 9 degrees, I need 0.9614 kilojoules. So if I put my 0.9614 kilojoules in here, and I'm trying to figure out what mass that I would need in order to what mass of methanol I would need to burn in order to heat it up by 9 degrees in order to release 0.9614 kilojoules. I'm doing a cross multiplication here again. I'm timesing those two things together and dividing by this number here. So 16 times 0.9614 divided by 24.6. And I get 0.63 grams. That is how much mass of methanol I would need in order to get a 0.9614 energy released to heat my water up 9 degrees.